Our company has been challenged to create a solar thermal collector. The clients live in northern Michigan. The challenging part about this design is that it has to be facing the sun as direct as possible throughout the entire year. Specifications have been required for our design proposal as follows. The solar thermal collector should heat a 1,200 square foot house. The house is located at a latitude of 45 degrees north, and the design has to be cost efficient, reliable, and satisfying.
So as stated previously, the design must be able to heat a 1,200 square foot house. It should do so while being as efficient and compact as possible. The solar panels must be able to create the power enough for the individual to heat their house independently. Being in Michigan, the panels and system must be able to tolerate the moderate to extreme weather conditions, while also adapting to the sun location, maximizing the efficiency.
We are constrained to a maximum amount of surface area, knowing that the solar panel will be mounted on top of a roof given its size. We also know that these solar panels have to heat a specific surface volume of the house. We also are constrained to the weight of our design because we don't want to be adding any extra strain or unwanted pressure on the roof, which would lead to costly damages. As well as the angle elevation is constrained, given that the sun is on a different angle at a latitude level of 45 degrees.
The designer's proposal for the design will look something like this. The solar panels must heat a 1,200 square foot house as known, so in total there will be 37 panels on the roof. Each panel will cover 17.55 square feet of surface area. Each panel is 5 feet tall by 3 feet wide, give or take a few inches. And in total, they will take up about 650 square feet of surface area on the roof. Each panel can produce 320 watts worth of power, and at that rate, with 37 panels, that's around 12,000 watts of power, which with proper insulation in a house could heat up a whole 1,200 square foot house. The panels themselves will be coated with clear poly sheeting so that they are protected against the elements such as rain and snow. The panels themselves are completely adjustable depending on the sun's position in the sky. So the way that works is we will be installing a set of ultraviolet and infrared sensors on the roof, all connected to an Adreno. And the Adreno will read the data that the sensors collect, such as ultraviolet lighting, the UV lighting reaching the sensors, and the waves of the infrared, and will adjust the height of the cylinder based on that.
We were able to achieve our goal of creating an efficient system by designing solar panels that adjust the angle of the sun using sensors and hydraulic cylinders to maximize the solar power produced. It is compact as the total area the solar panels cover is only 650 square feet. This is enough power to heat a 1,200 square foot house.
In conclusion, each solar panel has 2 hydraulic cylinders that raise and drop the solar panels according to the location of the sun, which is detected using a combination of ultraviolet and infrared sensors for the purpose of locating the sun and adjusting the solar panels to a perpendicular angle, getting the most energy from the sun.